There we go. Now you gotcha. Welcome, Thursday. I'll tell you what, it is a busy day today. Just had a phone call with my application engineer down in Texas. He had a good question on motors. I had some transformers I had to get some orders in for. Felix Sandoval, yes. Thank you. I got your email, brother. Cool picture, cool. So I appreciate you sending the pic as well. And if I have some time, I'll try to grab it and show everybody. You got your Shark Week mug. So thank you, sir. I appreciate that. Appreciate the email, and I read it to my wife too. So she was happy, and it was good to see you. Good to see you. So I just got to share one other thing here, and we are going to continue our discussion. I got to get my bearings in order because it's like boom, boom, boom. You know how it goes. So we are going to continue our discussion on the single line diagram. Newsfeed, public, post. Oop, I'm just posting it. All right, close that. We got a feed. I'm only going to YouTube right now, so makes my life a little bit more simpler. I can see everybody's feedback. I just posted the links to this on my LinkedIn and Facebook, so that's out there. That's out of the way. And let me close this. Man, all right. So, see now, where were we last week? If I'm not mistaken, and I'm developing this PowerPoint slide deck, so you guys are all a part of this. You gotta love it. This is why I love going live. It just makes we're killing a bunch of birds with one stone. Okay, put all that down. You got your water, you got your coffee. So hopefully you got all that taken care of. Remember where we were. Let's just do a quick review. We were talking about this one-line diagram. We made some changes to the single-line diagram to address some incident energy and implement some basic design parameters. But what I wanted to do was get us back to square one on this, and not worry about right now about rearranging the one-line diagram. So we're going to take SKM and we're going to run what they call scenarios in SKM, which will give us the ability to make some changes and see what the impact is without losing our original design. And I'll show you what I mean by that. Ryan Jackson in the house. Good to see you. Ahmed Mahdi, thank you for joining us. We got Robert from Omaha. Was just talking to him too. James Smith, you are the man, brother. What's up? Pop the clutch, man. Amen. And Dimitri Cobain. See, your Dimitri is the beginning of Dimitrovich. So that's a good thing. We got something in common. At least I say Dimitri like I always say Dimitrovich, and everybody spells my name wrong. So anyway, we are going to, what we did, remember the base, I do have to tell you, we have one fix in here. There was an individual who told me C3, you see C3 impedance? That is wrong on the diagram, and I'll tell you. I remember I put a link into the to this page, and what we're going to have to do right now is fix. Okay, we're going to take these impedance diagrams, and I have to fix the conductor 3 impedance is not 0.00. What I did was I copied. Take a look at the impedance of the utility. I must have copied it down for conductor 3 and I did not change it. So we are going to do that right now. I've got to make sure that that is correct. The correct impedance is 0.0449, 0.0449, see it's changing, plus J 0.0299, 0.0299, and that basically works out to be a Z of 0.0539 at an angle of 33.66. All right, so we fixed that. I'm going to copy that and just make sure that, yeah, it's wrong on the next page too. I'm fixing that. I'm just going to fix a couple pages in here because that would not be good if you're trying to do this math and I've got the wrong numbers there for you. So I'm doing what I can to make it good, make us good. All right. So that's a fix. And thank you. I can't remember who it was who made me aware of that. But that's what we call teamwork, right? So we're all engineers, or well, some of us are, but we're all in the electrical professional. We're all human beings, and we will make mistakes, and we need to check each other. So thank you for that. All right, so what I want to do today is we went through, and remember, this is I don't prep for this too much. So we went into SKM and we started picking overcurrent protective devices. And remember, on a transformer, when we picked our primary breaker on this T2 transformer and we picked our primary fuse on T1, we had, because we're following the rules. Remember, when we're picking the primary overcurrent protective device, we've got to take into consideration the inrush current on a transformer. The National Electrical Code 450 tells us we can go up to 250% for that low voltage transformer down there. The highest is 250%. The lowest is really dictated by the inrush current. I'm not going to go at full load amps because I'll trip that breaker every time I energize it. So in reality, I mean, we'll start off with 1.25, and I know a lot of our transformers, and what we read last week was that that those transformers, when we design, I know Eaton has a paper put together that says we're trying to design our transformers so that you can use 1.25. That gets you into a smaller breaker. But there are cases where, depending upon depending upon the waveform, where you're at in the waveform when you close in on it to energize it, you could be drawing a little bit more inrush. So it might be hit and miss, And my guess is that if you're trying to energize a transformer and you keep tripping the breaker, and it may be on the third time it holds in, I would say you're cutting it really close on the instantaneous. So you might want to take a look at, those are the types of considerations from a reliability perspective. You don't want to have to keep closing in a circuit breaker just to get it to hold because of that inrush current. So, it's just I don't know. It's up to you and your design, but you can avoid the repetitive nature of close it, let it trip, close it, let it trip, close it, and it holds. But if you just, think about that instantaneous pickup, think about the transformer inrush, and maybe go up. Instead of doing 1.25, go a little bit larger, go to the next larger size up from that. That might make your life a little bit more simple. All right, so this is the one-line diagram, and I'm going to show you real quick. I don't know what tool you're using. Like I said, in my opinion, these software applications are like if you're an Apple person or if you're a Microsoft person. If you always use Microsoft, you think about the Windows environment. You're thinking about file storage. When someone gives you a MacBook Pro, they do things differently in the Mac world. So you might get frustrated and go, I like Windows. Well, you know what, the reason you like Windows is because that's what you were trained on, that's what you're familiar with, so that's what you use. So I cut my teeth on SKM. I use SKM. I know this interface. I'm familiar with it. I can navigate it very quickly. You put me in front of another application and I'm going to be on a learning curve. So that's why I use SKM, but I personally, I like it. So, but I can't tell you the difference between this and EDSA, Easy Power, and other tools because I don't have familiarity with that. Now, what I'm going to show you in this application, there are probably ways to do that in Easy Power or one of those other applications. So, or hopefully there are, because I love this feature. And you know what? I learned this feature. I learned this feature by mistake well after I've been doing this. I've been using this tool for a lot of years, and I never even knew it existed until I asked somebody for some help on a project. And I said, hey, can you come up with the right solution on how, from a selective coordination perspective, trying to come up with different options for my customer? And he came back and he opened up his computer, and he was like a student of engineering, I would say. And he started to use this tool where he went to project and he went to this thing called Scenario Manager. And he created a few scenarios. So if I go to base project and you bring up one of these topics up here, if I make any changes, it'll highlight the changes that I made. And if I do this and I say, you know what, I'm going to go back to the original, I go back to Scenario Manager and I go to original and I activate. And now I've got that same one-line diagram. But when I click on, let's see, cables. Nope, I'm going to find one that I changed. Here, okay, see this where it says bus 4? It's highlighted in red. That tells you, what I did was I started this scenario thing after the fact because we made changes last week. And then I thought, well, shoot, I want to do ground fault calculations with you. And I want to use the original impedance diagram and just say, okay, take that impedance diagram, you know, take this diagram here, this impedance diagram, and redo it. And redo this for the ground fault calculation so that we can work on positive, negative, and zero sequence and show you how to calculate ground fault current. So and how to get this impedance diagram to give you ground fault current. And I didn't want to have to go through the per unit again and recalculate conductor impedances. So I wanted to get the SKM back into the original format, this one. So after the fact, I went and modified what we did last week and just put this back. So I had to delete some buses, which means that this conductor, remember, I connected it to a intermediate bus so that I could put an overcurrent device and then another conductor, because what I wanted to do was reduce the incident energy at that first panel board by putting a breaker in the box in a separate enclosure, to show you now I can reduce the incident energy at this panel board. And remember the concept of moving the energy. So I used that as my base and I got it back to the original. So this document, this SKM package right now, this diagram is where we started on our journey. And what you'll be able to do now is basically we'll be able to, after we get done talking about the right overcurrent protected devices, after we get done talking about the ampacity of the conductors, because remember, one of these conductors, I have 5 750s in parallel. Well, I picked those 5 750s based upon the full load amps, but yet we increase the size of our overcurrent protective device. And I've got 5 conductors in a raceway conduit, and we got to figure out what's the fill. We got to figure out what size conduit would I need for 5 750 MCM conductors. And then if I have 5 of those in a raceway, what's the ampacity? And do I still have the right ampacity, or do I need to change my size of my conductor? Right? So we didn't even think about that. Well, again, this is a journey. And the first step is to establish the size of the overcurrent devices. This is the way I do it. With a transformer, that primary overcurrent protected. Now the secondary device, I put the panel board I want on it. Okay, I know I can go greater than the full load amps of the transformer because I can push it hard if I want to. But for the secondary, I can establish what the size panel board is. If it's an 800 amp panel board, I put an 800 amp overcurrent protected device, I'm golden. But the primary of this transformer, I'm going to pick the overcurrent device based upon the inrush current, not the full load amps. And then I have to make sure that my conductor is not sized to the full load amps. My conductor is sized to the protection, because remember, Article 240 tells me I have to protect a conductor at its ampacity. So if my transformer's full load amps was 300 amps and I put a 400 amp breaker on it because I wanted to allow that inrush, I wanted a larger size breaker, then I can't have 300 amps worth of conductor. I need 400 amps worth of conductor, even though my full load amps is only 300 amps. Okay, so, and why? Because I picked a 400 amp breaker. So I want to cover that, and I want to do, I'm going to work through a conduit fill calculation, and I want to work through an ampacity calculation, and then we'll make some adjustments to this. We'll make a scenario. We'll take this one line right here, and we'll do I'll show you. I'm going to go Project, Scenario Manager. I grab the original and I say clone. And now I have a scenario 3. I'm going to rename it, and I'm going to call this, what's today? 2021 0304. That's today's date, and that will be the scenario that we'll work on. Now I have to click on that and then say activate and exit. And now I'm in. And basically what it did, if you looked at your SKM folders on your computer, it created another folder with this file name on it, folder name, and then in it are all of the one-line diagram, your reports, and everything else. So now you're completely in a different scenario. I can make any modifications to this. It's not going to change my original scenario. It's going to be what it'll do is it'll highlight for me all of the changes I did make. So I know what I changed, that I changed it, and then I'll be able to run it. So I'll go back over here to one-line diagram, and you'll see it says scenario 3. I say open. There's my one-line diagram, which is basically the same as what I had before. And now what we're going to do is we're going to focus on this transformer. Now remember, we had a So right now I've got a 600 amp. I've got a 600 amp breaker, right? And why did I pick a 600 amp breaker? My primary full load amps was 360.8. 360.8. 1.25 is 451. That means if I just did the 1.25 and I said, well, I'm going to go to the next higher, I can go to 500 amps. I moved it to 600, and let's see why. If I'm going to grab both of these, and I'm going to go to TCC. I'm going to call this T2 primary breaker, and what I have to do now is I have to change this to multiple of 10. So everything at the bottom is going to, the whole curves are going to shift over to the left. And I did not select my breaker, and my breaker number is PD11. Why? Because it goes to 11. So I do existing, and I'm going to add PD11, which will be my primary breaker. I hit OK, and there's my breaker. And look at where my Inrush, my instantaneous is. Okay, so this is a it's a thermomagnetic circuit breaker. What is it? It is a Cutler Hammer Eaton HLD breaker. So it's an L frame breaker. I can adjust the instantaneous down if I wanted to, but it is a 500 amp. So I did go with a 500 amp breaker. For some reason where did I have 600 amps? Oh, it's a 600 amp frame. And it's at 500 amps. So it's a 500 amp breaker. So I got 500 amps, and that was actually the recommendation of from Eaton perspective. So I went. You should always go back to the manufacturer and see what their inrush currents are and what they recommend and all that good stuff. So we got Nihad El Sharif is in the house. Thanks for joining us, brother. All right, so we have this, and there's our Inrush current. And what did we do for Inrush? We set the transformer Inrush at 10 times. The Inrush factor is 10 times. So, and you can get that information from the transformer manufacturer. In some cases, it might be higher. So it depends on the efficiencies of the transformer. It depends on the transformer's winding and the manufacturing and all this other good stuff. So you should consult the manufacturer's information to figure out a ballpark figure on where they lie on the inrush, because that's going to dictate that X on your curve, and that's going to dictate the instantaneous pickup. So in this case, I'm at 500 amps, and if I look at my that's the frame, is a 600 amp frame, 500 amp trip. So I'm at 500 amps, but my ampacity of the conductors is 450. I got to have, I want to be protecting the conductor at its ampacity. So I've got to do something about this conductor. That's a 3/0 conductor. If I go to 310.15, if I want 500 amps worth of conductor, what am I going to use? Shoot them out. I know we got, who do we got out there? Ryan Jackson. Ryan Jackson in the house. So 310.15b 16. I would probably want to go with so what have I got right now? I've got two 3/0. That's 400 amps technically. And so that's the other thing. So that ampacity says 450. What they're using is the 90° C column. I can't use 90° C column. Why can't I use 90° C ampacity? I can use a 90° C insulated conductor, but because I'm landing it on that breaker, I've got to use the 75° C column. So you got to be careful. And I'm not sure. I've never used SKM's checks and balances. I've always done my own math. So this conductor is only good for 400 amps. So because 3/0 is 200, two of those is 400. I had to do the math in my head. It's a lot of math to do. So I need 500, so I could do two 4/0, right? So if I, because the 4/0 conductor is 230, I can do two 250s. Or, there's a question for all of you out there. There's multiple ways to get to the amps that you need in conductors. What do you use to determine the size conductors? Do you use 4 of one size? I mean, does it depend on what you have in stock? Does it depend on what you can easily get from your supplier? Does it depend on how many you're going to have to pull through a raceway? I mean, I could put to get 500 amps, I could put two 250s. So two 250s will get it for me. And so here's what I'm going to have to do. I'm going to have to do two 250s. If I do two 250s, the same footage, I got to go back to the impedance, and here's what we did. 110/14C2, parallel 250s. There we go. So we parallel two 250s. That's what we would do. Good idea. Great minds think alike. Now, what I've got to do is look at the impedance. Now, this is what is loaded into SKM. A lot of people will just simply take whatever the software application. So Ryan is 110/14C1. Let's just, for everybody's sake out there, let's just read for everybody. 110/14 is your electrical connections. C is your temporal limitation. 1 is equipment provisions. So this talks about the conductor ampacities and rated what amp, the 75-degree C column and all that good stuff. So in any case, now the impedance values. If I look at a 250 back in Table 9, remember Chapter 9, Table 9 gives me my impedance values and why impedance values are important for short circuit calculations, right? What SKM uses is 0.0552. So 250s resistance is 0.054 in the book, and then the X is 0.052, and they have 0.049. So what I'm going to do is I'm going to override this. I unlink it to the library, and I'm going to just follow this. Now you can do whatever you want to do. You can use what's in your library, and that's probably preferential. Or if you know from the manufacturer, James Smith, I'm on Table 9 in Chapter 9 of the code and looking at the impedance values. So if I look at 750, so what I'm going to do is I'm going to put what's in this book in here. So resistance, and this is in the back of the code, Table 9, Chapter 9, I'm on page 70-706 of the 2020 NEC, and the resistance value in steel conduit for copper is 0.250, right? These are 250s? 0.054. 0.0, there I go with the 0.0054. So that's my resistance. And my X impedance is 0.052. 0.052. Okay. I'm going to give you we're going to talk a little bit about positive, negative, and zero sequence right now, your symmetrical components. Let me know your preferred. All right. I think we're doing some testing. So you'll see the zero sequence impedance is different than the positive sequence impedance. When we start to do ground fault calculations, zero sequence impedance is going to be important. If we think about positive, negative, and zero sequence conductors, I'm just going to do this and do this, this, this. All right. Positive sequence. Positive sequence, I would draw like this. And this is A, B, C, 120 degrees from each other. And that is 240 degrees. Okay? Now, negative sequence, and I'm going to explain this a little bit as well as we go along. I'm just giving you little bits of information. I haven't even talked about what positive, negative, and zero is. Some of you may know, some of your power systems guys may know. This would be A, and then this would be B, and this would be C. That's again 120, and this is again 240. But I'll be mindful that the rotation is different. Positive sequence is ACB or ABC clockwise. Negative sequence is ACB clockwise. So you have one sequence going this way and the other sequence going the other way. And how positive and negative sequence was first, I would say, discovered or used with regard to motors in understanding the heat generated in a motor, because they noticed that there was this other sequence of currents that could flow that could create heat, which was in a different phase rotation than the positive sequence. Now, it wasn't until Fortescue, C.L. Fortescue, I don't know if C is for Chucky, or if it's for Charlie, or if it's for Calhoun, I don't know, but it's C.L. Fortescue. He discovered and he came up with the positive, negative, and then the zero sequence is basically, zero sequence is 1, 2, 3. Your A, your B, and your C all in series with each other. They're at the same angle, so they're additive. It's not opposite rotations or anything like that. So what Fortescue did was he found a process for us to take an unbalanced system and evaluate it as a balanced system, separating it into a positive, negative, and zero sequences. It's a mathematical process, I would say. Each positive sequence voltages and impedances don't impact negative sequence voltages, impedance don't impact zero sequence voltage. So they operate independently of each other. We use the term zero sequence current transformers, CTs, and it's because they're all in phase and they add up with each other. So we know that your positive and negatives and whatnot, all your A, B's, and C's, if you do the math, they will all add to zero on a three-phase system. But when they don't add to zero, you're into your zero sequence, and that's where you get that's what's detectable by the zero sequence CTs, etc. So zero sequence, when we start to think about our system as an impedance diagram, positive sequence, what I'm showing you all here is positive sequence impedances. And we'll use positive sequence impedances to calculate the three-phase bolted fault. Negative sequence impedances, for all intents and purposes, what we assume is that they are equal to each other. So if you create a positive sequence diagram, it is equal to the negative sequence diagram. The difference from a symmetrical components perspective is the zero sequence. Now, not only is this diagram going to be different, but also some of your impedances will be different. Hence, what started me down this road with each of you, the impedance values in the SKM software or in EDSA or whatever application that you're using, Easy Power, they've got to give you an avenue to put in the zero sequence impedances, especially for conductors, because the zero sequence impedance of a conductor is going to be different than the positive sequence. And if you, a reference that you'll want is this book right here, Symmetrical Components. And Wagner and Evans, you know what's really cool is when I look back, you know, these guys are like my heroes, right? So C.F. Wagner was a central station engineer at Westinghouse Electric Corporation. Evans, he was manager of transmission engineering at Westinghouse Electric. And Fortescue, there's an introduction in this book from C.L. Fortescue, and the date of this book is 1933. Symmetrical components hasn't changed, and it won't change. So these books are still good, especially if you're a power systems engineer, because this stuff doesn't change. So this book, they have chapters in here for each of the types of equipment. So you'll like, for example, transformers. They talk about the different transformers. They talk about the impedance to zero sequence. And in here, they'll tell you that the zero sequence impedance of a transformer is same as the positive, is same as the negative sequence. So when you're doing your impedance diagram for calculating ground fault currents, your positive sequence is your impedance of the transformer. Your negative sequence impedance is the same as the positive sequence for that transformer. And your zero sequence is the same as the impedance of that transformer for positive and negative. So that doesn't change. But in here, they also get into the discussion of conductors. Now, the conductors, I'm not going to look it up. It's complicated. There's I think there was a movie about it this way too. The issue with conductors is that the zero sequence values of impedance are going to be dependent upon the diameters of those conductors, the proximity of the conductors with each other, and whether or not it's in raceway, whether or not it's in metallic raceway as opposed to PVC raceway. So all of those factors come into play when you start talking zero sequence impedance. Now, SKM, and I'm not sure about others, but SKM software will use, this is their paper. If you go out to the SKM support, they'll tell you that the title of this is Zero Sequence Impedance in Cables. And they tell you that if your conductor is in magnetic raceway ducts, R resistance is 3.1515 times the positive sequence. If it for zero sequence reactance, it's 2.4617. Now, what I'm trying to do when I'm researching right now is I want to, and eventually I'll figure this out, but I want to verify those numbers. I want to figure out how did they come up with 3.1515. They don't tell you how they arrived at that. So I'm that's a part of my journey. I'd love to figure that out. And if you're into the zero sequence and you got the resources, if you figure it out, please bring that to the table. I'd love to have that input from you. So in any case, what I've got to do then, knowing that, and I'm going to do this because I've already done it for the other conductors, I'm going to take my resistance 0.054 and I'm going to multiply that by 3.1515, and that is 0.1702. And look, it's 0.17 instead of 3902, and 0.052 times 2.4617. 2.4617. And that's 0.1280. 1280. All right. So I have changed my conductor size. I've changed my impedance. And now I am protecting that conductor at its ampacity. Now, what we're going to do is I'm going to focus in. Now, this is on the primary side of the transformer. Remember what I said. Changes on the primary side of a transformer, like from a utility perspective, I can have wide changes in available fault current at the primary side of the transformer and very little effect on the secondary. I increase the size of my conductor on the primary, reducing its impedance. And now I'm going to see the impact on the secondary. So I haven't run the calculation yet. So I have 12,000. I'll write this down. I need my talking paper. So we have 12,844 amps of bolted fault current at bus 7 before the change. Now we're going to run control, and let's do ground fault too. My ground fault is 14,010. Now we're going to run our math. We're going to do control A, and we're going to run a short circuit. We're using ANSI. And I hit close, and it went to 13,043. Not that much of a difference, right? So I went to 13,043, 12,844 minus 199 amps. So, and this goes back to my discussion from one of my earlier classes, and I have a whole nother program on transformer protection. Changes of available fault current on the primary of a transformer do not have as much of an impact on the secondary as a lot of people think. Okay, so we changed that. I'm not going to worry about the interrupting ratings, because if I picked an interrupting rating of my overcurrent protective device right here, based within 200 amps of the available short circuit current, that's my bad. I shouldn't be doing that. I got to give myself some breathing room, not just for the initial design, but for the life of the installation. I've got to be thinking about what happens if they add motors. What if I added a motor right here on bus 7? Now this overcurrent protected device could see more fault current, and I could easily run into the interrupting rating. So I should never be picking an interrupting rating that close to my calculated available fault current. We could have an argument. We can have a debate on do bolted fault currents occur? Rarely. They could. I'm sizing this, and you could say, well, regardless, it's probably not going to see a bolted fault current anyway. So if I exceed that number, who cares? Your inspector is going to care. Hopefully, your plant manager is going to care. And we've got to just do the right thing. So, in any case, what I did show you is changing that conductor size on the line side is not impacting me as much. So if I had a change in the field, as per my as-built drawings, and they said, hey, Tom, we put more conductors, or we changed the conductor size because you screwed up on the ampacity calculation, which we still haven't done, right? Well, on this one here, I don't have to worry. I have two conductors. And what does 310, 15, what's the section, Ryan Jackson, 310.15 C1 tells me number of conductors in a raceway, the adjustment factors, 4 to 6 conductors is where I start. Not more than 3 current carrying conductors in a raceway for table 310.16. I've got 2. I'm looking good. So I don't have to worry about adjusting the ampacity of this conductor. I've already adjusted for my overcurrent protective device. If ambient temperatures, I'm not going to deal with that, but you can deal with that yourself, making your adjustments there. What else would impact the size of this conductor? I don't think anything else. So that conductor looks good. This conductor is, I've got 800 amps, and how many do I have? 2, so I'm good. Just make sure how many I have up here. I've got 2, I'm good. Okay, let's look at this one. I've got 5. Okay, I got 5 750s. I need 2,000 amps. I need 2,000 amps worth of conductor. Ryan, are you still out there? Because I'm going to ask you a quiz question, buddy. You got to adjust for a voltage drop. Yeah, there's another adjustment. So you got to do your voltage drop calculation. I'll leave that to the student. I have 5 conductors. can I put 3 raceway, 2 conductor in one, 2 conductor in another, and 2 conductor in another? There's a question for you. Robert from Omaha, Ryan Jackson, Nihad El Sharif, James Smith. I want to take 5 conductors, put 2 in one raceway, 2 in another raceway, 1 in another raceway. Is that permitted by the National Electrical Code? What section? What did Mike say? Mike Holt says, you're the professional, you can do it. Check it out. Let me know. Well, what I'm going to do right now is I'm going to determine for a 750 KC mill, 5 of them, what size raceway could I put it in? How do I do that? I have to do a conduit fill calculation. Now, to do a conduit fill calculation, let's just do this. Control C, V, 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 V. Somebody asked me how I was doing my whiteboard. What app was I using? And what I had to tell them was I'm using PowerPoint as my tool. And what I'm doing is I am sharing my screen on another computer. I have PowerPoint open. I'm using my little pen because it's a touchpad. All same phase, yeah. So I'm going to have A phase in 3 separate conduits. A phase, I have 2, 2, and 1. Yeah, baby. 310.10H. I love it. I love it. You guys are good. So let's read 310.10H. Love it. Man, this is what I like about working with professionals. 310.10 is uses permitted. 310.10H is... Boy, my eyes are going bad. Not H. G, right? 310.10 G what? Yeah, G. So if you look in G, when you see conductors in parallel, it says that conductors in an installation, the paralleled conductors in each phase, polarity, neutral, ground, circuit, conductor, equipment, blah, 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 shall comply with be of the same length, consist of the same conductor material, be the same size, have the same insulation, be terminated in the same manner. But also aluminum, if you look at G1, shall be permitted to connect it in parallel. Where is it at? Conductor, the paralleled conductors in each phase, polarity, blah, 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 or equipment branding should comply with the following. There it is, separate cables or raceways. So this is 3. Where run in separate cables or raceways, the cables or raceways with conductors shall have the same number of conductors and shall have the same electrical characteristics. So, hey, Mohammed, so if I have a raceway, that has 3 raceways, 2, 2, and 1, that would violate 310.10G3, separate cables or raceways. So I'd have to either throw another one in there or do an adjustment. So I need an even number of conductors. So what I'm going to do is say how many 750s. Now I went closed book. So the question is how many, I have 5 750s. What's the conduit size you would use? Now, how do we do conduit size? So I have 750 MCM. I've got 5 of those, right? So the first thing I got to do is go back to Chapter 9, not the informative annex, but Chapter 9. I got to figure out my circular mills for a, let's take a look. What conductor am I using? I'm using, say, I don't know, THHN? Or how about this? How about XHHW? Yeah, so then we'll say XHHW. Okay, so XHHW. Now I want to figure out how many of these I can put in a raceway. T4 and 5, Chapter 9. Tables 4 and 5, Chapter 9. That's right. I'm in Table 5 right now, Chapter 9. And I'm looking at 750s. Millimeters squared is 679.5. So 679.5 millimeters squared. All right. So 679.5 millimeters squared. I've got 5 of them. So if I take 5 times 5, 679.5 is 3,397.5. 397.5, right? So that's my total circular mils area for that, those 5 conductors. Now I got to figure out what size raceway what conduit? EMT. I want to use EMT. EMT. Easy as 1, 2, 3. So I go to Table 4 in Chapter 9. Table 4 is going to give me my, in fact, Table 4, the first one on page 70-696. There's my EMT, electrical metallic tubing. Your installer will never forgive you for specifying 750 copper. I trust Tom's muscles will be there to land it. Ryan, come on. I mean, give me a break, brother. Get the guns out. Bobby Joe could pull these. Come on. Okay, so what do we know? If you have, what's the minimum percent fill or maximum percent fill? Maximum percent fill for over 2 wires in EMT is 40%. So 40%. So what I would do is take 3,397.5 divided by 0.4 is equal to 3,397.5, 0.4 divide 8,493.75. EMT is tubing, not conduit. Tubing. That's right, it's tubing. It is electrical metallic tubing. That is correct. It's not IMC for conduit, it's EMT for tubing. Okay. If I look at the total area, which is the very last columns on the far right, if I, what do I have? 8,493. I got to find a number over there greater than 8,493, and that takes me to 4-inch. So Ryan Jackson, can you bend 4-inch conduit? I mean, they make it, brother. Okay. Now, what are the other options? If you didn't want to do, what did we say? How many? We've got 5 750s. 5 750s. I need 2,000 amps. Now, if I'm going to put all of those in one raceway, let's do our ampacity calculation. 4-inch, baby, yes. Let's do our ampacity. Let's do our ampacity calculation, right? So ampacity is based upon conditions of use, right? So, forgive me for my very bad, this is a whatever. Okay, so I need 2,000 amps. Right? Is that 2,000? Yes, it is. 2,000 amps. So what do I need to do? I know I've got 5 conductors. I exceed 3. If I look at table 310, so I got to go to table 310.15, Charlie 1. That is in the, you know, there's an off switch on the side of this. And every now and then I will accidentally hit that and shut this off. Are you installing a wire type EGC? Need to calculate that as well. If using the Steel Raceway, just use Annex C instead of Table 4. Very good, Ryan. Very good. Let's just take a look for everybody. So he says Annex C. So we're going to just for everybody's Annex C is an informative annex, and basically it has the trade size, it has the type of conductor, the conductor size, and the different size metric whatever size conduit raceway, right? And for EMT, so you can, and it accounts for everything to Ryan's point, but I believe you can still use a table, a 4-inch. Anyway, double check that for me, Ryan, if you can. I believe 4-inch is still good. But regardless, we got to talk about ampacity. So 2,000 amps is what I need. I know I got 5 conductors. Per this table, my multiplying factor for 4 to 6 is 80%. So I take 2,000 amps, divide that by 0.8, 2,000. 0.8 divide is 2,500. So I need 2,500 amps of conductor. If I look at 750 MCM is rated at 475 amps. 5 times 475. 475 is 2375. Can't use that. It's 2375. So I need at least 2,500 amps. So I can't do 5,250. So what I can do is say 2,500 amps, 2,500, and I'm going to divide that by 6, 416. I can use 6 600s. 6 600 MCM will give me what I need for 2,500 amps. Does that make you feel better? It's a little bit better than 750s, Mr. Jackson. So let's change that. Let's just see what happens. If I do this, and I'm going to have to go back to my library, and I'm going to pick, I'm going to go down in size and up in number, same thing, and I have to disconnect the library, go back to impedance. I'm going to change my impedance values. I got to go to table 9. Check my numbers there, Ryan. I'm going to go back to chapter 9. Chapter 9, table 9, and I'm looking for positive sequence. R for 600. R is 0.025. 0.025. X. Tubings. Let's see. X is 600. 0.048. Okay, and then I got to put my 0 sequence in. What did we say the numbers for 0 sequence were? 3.1515. 3.1515 times 0.025, 0.0788, 0.048 times 2.4617, 0.1182, 0.1182. Hang on, I think you were using the 75. Oh, ho, 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 ho. Dadgummit. Yeah, you're right, Ryan. Hold on. You're right. You're right. I was. Okay, what Ryan Jackson is pointing out, I can use the 90 C column to do my calculations, but I can't exceed that 75. So let's do the math again. So 750 is 535, right? 0.8 divide 5 times. We're 75. I can use the 90 C column. So, all right. So I've got 4 to 6. So here's what I needed. I needed 2,000 amps. So I need 2,500 amps. So if I do 5 750s, yes, I can do 750s. I don't have to change anything. I can do 750s because if I do the multiplication by the 90 C column, is that right? Yeah. Yeah, but I'm limited by the something doesn't smell right, Ryan. Something doesn't smell right. So if I do my I know I need 2,500 amps. If I use my 90 C column at 750s and do 5 times 535, I'm good. I'm good to go. So that should be good. I'm good to go. So I don't have to change this. I can put this back to I can put this back. How do I do that? I got to go back to the library. I'll reconnect. Gosh darn it. Go back to 750s and go back to 5. And I've got to disconnect. I got to go back to my impedances. Go back to the 750s. Good catch. And that's why we got Robert from Omaha and Jackson in the house. 0.021. Let me get a book. All right. You better get a book. I mean, you don't come to one of my programs and you don't have a book. Get a book. We're going to put this back at 0.021. And we're going to put the no, that's 0.021 is the resistance. And then 0.048. Putting this back to 0.048. And then I'm going to do my math for the zero sequence. Remember what that was. Remember what the impedance was for. So I'm just doing my my library is what I'm doing over here. So 3.1515, 3.1515 times 0.021, and that's 0.0662. 0.0662, and then 0.048 times 2.4617, and that's 0.1182. 1182. So that covers our positive and zero sequence, and we're going to need the zero sequence again to do our ground fault currents. All right, so run balance system study, run, Forrest, run. So none of that's changed. 29,872 still looks good. All right, so we've got those two conductors taken care of. Did we do the primary of this transformer? So this is this transformer 1 is a medium voltage, right? So if I go to 450, I'm using table 450.3a and not 43b, because B is for transformers 1,000 volts and less. Yep, 5750s. Yeah, and I thought that was right too, but good. Thanks for checking that for me, Ryan. So we are good for 5750s. All right, but you understand what we did. Just go back here. We have 5 conductors in a raceway. When you do your ampacity adjustments, you can do that off of the 90° C column. The mistake I made, and it's just been a long day, and we're all prone to mistakes. The mistake I made was I used the 75° C column when I did my backwards math. Remember, I did the 2,000 over 0.8, and then I used the 75° C column. I should have used the 90° C column. When I use the 90° C column, I'm good to go. So that's why that worked out that way, and I'm good with the 750s. Hopefully you got that one. All right, so now let's look at the 4160 to 208, a 4160 to 480 volt transformer, 1500 kVA. The primary full load amps is 208.2. What cable did I use? I'm using 350. What's a 350 worth? A 350 75 degree key. A 350 size MCM 75° C column is 310 amps per table 310.16. But I can't use table 310.16, right? Or can I? Yes, I can. They're going to be offering an offline solution in the near future too. Muhammad, I agree. What did Muhammad say? I'm spoiled. I have the NFPA link access. Yeah. Yep. All right. All right, so 350. I got 50 foot of that sucker, right? Let's just take a look what I've got. I picked, let's do this. Let's do this and this and this. I selected them both now. I'm going to go to TCC, and we're going to go T1 primary protection. And there's my fuse. Whoa. Whoa. So here's my my time current characteristic curve. I picked a primary fuse size of 300 amps. Is that good? What does 450 tell me? I'm going to do any location. So Article 450, Section 450.3a, Table 450.3a. Any location. Transformer rated impedance is 5.75. So it's not more than 6%. For a fuse, I can go up to 300%, and it says C Note 1, where the required fuse rating or circuit breaker setting does not correspond to a standard rating or setting, a higher rating or setting that does not exceed the following shall be permitted. I can't exceed the next higher standard rating or setting for fuse or circuit breaker at 1,000 volts or below, and the next higher commercially available rating for fuses or circuit breakers above 1,000 volts. All right, so I'm above 1,000 volts. And it's the next commercially available rating or setting of or fuse. So I can go up to 300%. What's my full load amps? What is my full load amps? Full load amps on this is 208.2. 208.2, and I'm going to do 1.25 because that's a good ballpark, is 260. I went to 300. And I plotted that. My inrush for that transformer, transformer damage, inrush is at 12 times. You know, I'm just going to leave it at 12. I would consult the manufacturer of the transformer to see, you know, is that right? And then I go, if I go to this, if I move it down, I could probably get away with a 250 amp fuse, but I don't want to. I don't want to be close to that inrush. It could be that my inrush current's less. It could be my inrush current's more. So I'm going to stick with a 300. Now I've stuck with a 300. That means that this conductor has to be at least 300 amps worth of conductor. And I'm using a 350, and a 350 is good for 310, so I don't have to change that. So I'm good. We good with that. I don't have to worry about adjustment factors. I don't have to worry about voltage drop. I don't have to worry about, well, I'm going to assume it's the ambient I don't have to worry about, because we don't know where we're installing this. So it's definitely not in an attic. So anyway, so that doesn't look bad. So I got that picked. I got that conductor picked. We did that conductor. We did that conductor. So I think we're golden. We got all of our conductor sizes. So I'm going to save this. Now what we're going to do, let's take a look at this. So let's just do an overview of what I've got. I have a transformer with a conductor, 15 foot, going to a breaker, which is a main and a panel board. The incident energy in this panel board, the incident energy here is going to be dependent upon not the clearing time of that overcurrent device. It's going to be dependent upon the clearing time of that fuse, right? Let's do a control A just to do a run. I make sure that all of that's Kovacevic. So I know I have a 29,000 amp, almost 30,000 amp bolted fault current here. And I'm going to run an arc flash analysis. So let's do that. Let's run arc flash. I'm going to pick bus plus protective device line side. So it's the line side. I'm going to use 1584 2018. Do the ANSI fault, not the comprehensive. Let's see what else. Fault currents, use global max, so 2 second rule. I'll use the 2 second rule. And then this is where device to report in labels, main device, last trip device. I'm just going to run it. I have auto update cleared. So let's do it. Let's just run it. I'm assuming you're ignoring the load side calculation. Mohammed, help me understand what your question is. Now, if you're thinking about, yeah, okay. So let's, if you're thinking about the load side of the transformer, here's what I did. If you think about this 1500 kVA transformer, the secondary full load amps is 1804. I have a 2000 amp breaker. You might say, hold on, Tom. You have a full load amps of 1804. How can you put 2000 amp load on a transformer? So here's the question. Well, here's my question to you. Where in the National Electrical Code says I cannot overload a transformer? Where in the National Electrical Code does it tell me that I can't exceed 1804 amps, which is the full load amps of that transformer? I'll save you some time because it's not in the code. So I can push that transformer greater than its full load amps. And if you look at 450.3b or 450.3a, since this is a 4160, it says the secondary protection, any location, circuit breaker, can be up to 300%. So technically, if I take 3 times 1804.22, I could put a 5,000 amp main on there. Yippee-ki-yay. I could put a 2,500 amp panel board if I wanted to. I don't want to, but I could. So that tells you what the maximum size secondary protection device is, and I would have to have the same, that protected of a conductor. So what I just did here, and we had this discussion before, what I just did was, look, I'm going to put a 2,000 amp panel board on the load side of this 1500 kVA transformer. But you might say, no, Tom, I would never do that. You might say, for a 1500 kVA transformer, I wouldn't even put a 2,000 amp. I'd put something smaller. You might say, heck, 2,000 amps. I'd put a 2,500 amp panel switchboard or whatever on there. So the code will let you go up to 300% on the secondary side of the of this transformer. So, and on a 1,000 volts or lower, it lets me go to primary and secondary protection up to secondary protection currents of 9 amps or more, 125%. So I can go to 125% on the secondary of a smaller transformer, or lower voltage transformer. Right, it doesn't care anything about that loading, and really, and the other thing you can think about, I could buy a transformer with fans and get more kVA out of it by cooling it. And another important thing from a short circuit perspective, let me find it. Let me find it here. I have a program that I did on short circuit calculations and actually transformer protection, I believe it was. Let me look at technical presentations. And because I had a transformer, and we're going to look at this real quick. Well, I don't know how quick it's going to be because I got to find it. Let me do power systems analysis, short circuit currents. Let me just see if it's here. All right. So this is short circuit currents. Oh, it's got to be in here. Oh, baby. Getting close, getting close. Yep, I think I'm smelling it. Yes, I am. I'm smelling it. All right, so this is from another presentation that I've done, that when you have transformers, you can add fans to that transformer, right? So this is what you'll see. You'll see these fans, and sometimes you'll see where it says FA or FFA. You know what FFA is? Future fans added. That means that there's no fans on it right now, but they could be in the future. All right, so we use a transformer cooling. So you show, and they indicate that most transformers are only loaded to about 40% or something like that. Rather surprising. Yeah, well, that's what they're saying there, Ryan, is if you think, I mean, just look at, and I think somebody else was doing a program on residential, and they said they put an ammeter on their house and they turned everything on. I don't know if it was Mike Holt or who, I don't know who it was. But they were surprised at how little current they were actually drawing with everything on. They weren't anywhere near 200 amps. So when you look at your load calculations, there's some beef in there. If you look at what we do in North America and even the standards, take a look at an IEC starter versus a NEMA starter. The NEMA starter is a lot bigger than the IEC starter is. The NEMA starter gives a lot more forgiveness in various parameters. So you'll get away with making some mistakes and things of that nature. So the load calculations, I think there's a little bit of fluff in there, and you know, it could be that these transformers are nowhere near the loading. So what you'll see on a transformer is AA for ambient air, AAFA for ambient air fans added, short circuit current calculations and equipment evaluation webinar. Yes, James Smith. FFA is future fans added, means it has provisions for fans in the future. So those are the types of ratings. The cooling, Onan the Barbarian, oil, natural, air, natural. What that means is you're not forcing the oil, so you don't have pumps on that transformer forcing the oil flow to get your cooling. And air natural is natural airflow through the transformer, but you may have fans which will force the air, or you may have oil forced air force, which means I've got pumps in there, pumps circulating oil in that transformer to provide the cooling. Now, here is a nameplate for a 4160 to 480 volt transformer, and you'll notice it says 3750 kVA / 5000, and the class is AAFA. So it's telling me when my fans are working, I can put 5000 kVA out of this breaker, or out of this transformer. It's been a long day. Now, so this tells me that I'm changing the full load amps. Now, think about it from your primary overcurrent protected device and your secondary overcurrent protected devices. If you're not sizing your devices to be able to handle 5000 kVA and the full load amps at those values, then your breaker is going to limit what you're going to put through this transformer. So you've got to make sure you're picking the right breaker and you're addressing when you have fans added. Now, I can have 3750 or 5000. I've not changed anything in this transformer other than I'm circulating air, and this is ambient air, forced air. So I've got fans on this thing, right? Now look at the impedance. 5.92% impedance. 5.92. All right. So 5.92% impedance. I have 2 kVA ratings. I've got 2 full load amps. Look at the full load amps is 4511 or 6014. There's your low voltage amps. I've only got 1 impedance. Important thing to remember. Just because you have fans does not mean you're changing the per unit impedance of this transformer. You're changing the full load amps. You're making that transformer work hard. But under a short circuit condition, you've got 1 impedance, and that impedance per unit is calculated based upon the AA rating, kVA rating. Because remember our base calculations, we did a base calculation. We took the kVA, we had to divide that by the voltage to get the full load amps. Divided by square root of 3, because it's 3-phase. I don't change, and then I came up with my base amps. I don't calculate a base amps off of the 5000. I calculate that off of the 3750. Because remember, this transformer, you're not changing the impedance is based upon the physical construction. You're not changing the physical construction when you add fans. All you're doing is cooling it so you can put more load through it. You're going to heat those windings up when you're drawing more amps and you're pushing more kVA through that transformer. And that's what the fans are there to keep the temperature at an acceptable level, you're not changing the impedance of that transformer during a fault condition. So don't make the mistake of doing your base values for your per unit calculations off of the 5,000 amp or 5,000 kVA, which is when you have the fans. Do it off of the 3750, the 480 volt secondary. You'll calculate your 4511. You'll calculate your base ohms off of those numbers, right? So remember, I need a base ohms, and then I do my per unit calculations off of that. So an important fact is that you're not changing that impedance. So, and that's a common misconception, right? So I just wanted to point that out. And this was our, that was my calculation. So in any case, 6:25, still got time. All right, so now walk through the secondary full load amp. Yeah, that's right. Yeah, so you're right. So I could, there's the secondary full load amps calculations. So 4511, I take 3750, not the 5,000, divided by the square root of 3, divided by 0.48, and I get my 4511 for that. And then my short circuit, maximum short circuit on the secondary is based upon the 4511 times 100 over 5.92. That gives me my 76,000. I don't take the 5,000 or the 6014 times 100 over 5.92 and say my short circuit current is greater when I'm on fans. No, I've got one impedance. All right, so don't make that mistake. You'll buy a bigger breaker than what you need, which I guess I wouldn't mind, right? I wouldn't mind that. Anyway, look at that. My sales guys are going, I'm losing orders. Tom's talking. Okay. All right. So what's the next step here? We went through, I saw Mohammed. Mohammed says, I'm assuming you're ignoring the load side calculation. Now, I don't know if you mean by the load calculation, because the other thing I'm not doing here is I'm not doing usually what we would do when we're doing a power distribution system. General philosophy, you start from the load, you work your way up to the service. So what do we do? When we're sizing the service, we're going to go through Article 220, and we're going to do a load calculation to size the service. I'm going to be doing my load calculations to determine the size of my panel boards that I need, the size, which will drive the size of the conductors that I need, which is going to drive the size of the transformer that I need. So I would typically, I'm going to do a general calculation to get the service, but then when I start getting down into the power distribution system, you'll probably have you'll know that for a typical building, you're going to buy these size transformers. There's a sweet spot, and it gives you a sort of a flavor. But you're going to have to do your load calculations to make sure that you're picking the right size panel boards and switchboards and all that jazz. Which we did not do because we just sort of drew what the stimulus for all of this was to teach you how to do a manual calculation of fault current, and now we're just building on it. All right, so we were doing the arc flash calculation. Now let's get back to arc flash, incident energy. What this is showing me, look, I've got two values of incident energy for each of these. Look at bus 4. So where's bus 4? Here is bus 4 is the first panel board on the secondary of this utility. I'll call it the utility transformer, but it's a transformer. Okay, we do special things for utility service equipment, and there's special hazards there, but that hazard is there because of that transformer for the most part. And it's harder to shut that off because you got to call a utility, so it's harder to establish an electrically safe working condition. But the issue of the incident energy at this panel board is no different than the issue of the incident energy at that transformer. They're based off the same principles. The clearing time is the upstream primary side overcurrent protective device, which we know we had to increase the size to deal with the inrush current. So I am adding an intentional delay on that primary. The code lets me go higher than what the full load amps is. So I'm putting a larger device than I probably would if it was just a conductor, right? So bus 4 incident energy is either going to be 77 calories. If I use this overcurrent device, PD12, it's 77 calories. If I use the primary overcurrent protective device, it's 106 calories. That's a big difference. Now let's look at some of these other parameters from an incident energy perspective. So hopefully these numbers aren't that small for you. I can't make it bigger. I don't believe I can. No, I can't make it any bigger. So let's look at what we've got. Look at the, so I have my bus 4, PD12 is what this is being dependent upon, and PD12 is going to be this breaker right on the secondary. The higher number is PD13, which is this overcurrent protected device, which is the primary fuse. I have my bus voltage. I have my bolted fault current value, 29.87 kiloamps. And then you'll notice, look at this. The arcing current is different. Why would it be different? It's the same bus. Why would I have 19.25 for 19.25 when I'm using PD12 to do my instant energy calculation, but 21.95 when I'm using the upstream fuse for my clearing time? The reason is IEEE 1584 has us calculate two values of arcing current. One value, and what we used to do in the 2002 version, remember, we calculated a value of arcing current and then they said take 80%. And we would calculate a lower value, and you would compare the clearing time of both of those overcurrent protective devices. Both of those overcurrent protective devices. Gosh darn it. So you take your TCC curve, and let's say that it's a circuit breaker like this. And I calculate one value of arcing current. Let's say it's right here, I arc. And let's say that the bolted fault current was right here. So what 1584 does is it gives me a bunch of equations. It gives me an equation to calculate arcing currents. And I calculate two values. In the 2002 version, you calculated one value and then you simply took 80% of that value to get IARC1 and then possibly IARC2. In the 2002 version, this was 80% of IARC1. In the 2018 version, Dr. Lee developed equations to calculate both of the arcing currents. How do we come up with the equations? So here's what we do. We take a box, and call it arcs in a box, and we basically establish and we create an arc flash event. We put all of these little calorimeters in front of it. We measure the current to get the sine wave and all that jazz. And then what Dr. Lee does is he basically says we're going to do a bunch of different series of events, and based upon parameters of X and Y, we'll basically get a bunch of data points like this. And you may say this is the minimum arcing current and this is the maximum arcing current. So you've got a band. And what he did before was he calculated this and said that the minimum arcing current is 80%. And that was a lot of error. So your minimum arcing currents were pretty low. Why? Because we wanted to make sure that based upon all the data points of arc after arc after arc and gathering all the data points, that the minimum arcing current that you calculated was not, you didn't have data points below that value, right? You want to be conservative. So what he did in the 2018 version is, instead of the 18%, he has an equation for that curve, and he has an equation for the minimum. So basically, your minimum arcing currents are greater than what they used to be. Hey, not Bill Cosby. Good to see you, brother. So you have two values of arcing current, and the reason that we do that, let's go back to this circuit breaker again. If I have my maximum arcing current is here, so I arc max, my clearing time is, say, 0.02 seconds, and let's say that my I arc minimum is here, my clearing time could be 0.07 seconds. What we would do is we calculate incident energy for that value of arcing current with that clearing time, and we would calculate the incident energy for that value of arcing current for that clearing time, and we would basically take the maximum incident energy, which could be generated by the lower arcing current at the longer clearing time. Right? Now, let's go back to this. Having said all that, for bus 4, we have 29,870 amps. When you're looking at the downstream breaker, this PD12, which is the 2000 amp breaker, that tells me that my higher arcing current is into a faster clearing time than my lower arcing current. So my lower arcing current will create a larger incident energy. So the first line item up here for bus 4, which is the clearing time, is based off of PD12, which is the 2000 amp breaker. It's using the lower arcing current because it has a longer clearing time. I don't have a way to blow this up. Let me do this. Maybe this is no, that doesn't change a doggone thing. I wish I could blow this up. How do I do that? You know what I'm gonna do here? Hold on. Let me just do magnifying glass.
I can learn to understand you much better if I can get familiar with the way you talk. I need your permission to help.
Maybe later. I don't know what that was, but my computer just talked to me. Magnifier. I do have a magnifier app. Hold on. Oh, Obi Juby Jubes. Hold on. Okay. How do I hold on. How do I do this? Views. Magnifier. I don't know. Nope. I don't know what just happened, but hold on. I'm going to close this. I'm going to close this. I'm going to bring that back up. Views. Lens. Oh, here we go. I don't know what that does. Oh my goodness. Plus. Hey, I got it. Magnifier. Who told me how to do that? Hold on. Who was that? You missed that, didn't you, 9? Who was that? Ryan Jackson, Mohammed. You can use Mohammed. Thank you, sir. Okay, so here it is. All right, so this was PD12, right? So PD12 is the downstream device. PD13 is the upstream device, the fuse. PD12, I have a bolted fault current of 29,870. My arcing current is 19,250. The reason they're using 19,250 is because on that trip curve, the lower arcing current gives me a longer clearing time, which will give me a higher incident energy. So the energy value that they're using here for 77 calories, for 77 calories per centimeter squared at a working distance of 18 inches and the arc flash boundary is 243 inches, is based upon the lower arcing current because it has a longer clearing time. For the fuse on the upstream fuse, it's using the higher arcing current. Why? Because look at the clearing time, 2 seconds. So look, it's the clearing time of the lower arcing current at the downstream device is 1.645. The clearing time for that upstream fuse, because the upstream fuse is so far to the right that the higher arcing current is going to have a clearing time of 2 seconds. The incident energy is based upon the higher arcing current and 2 seconds clearing time. So that is why the incident energy is up there at 106 calories per centimeter square. Do lower arcing currents always have longer clearing times? Depends. So I would say if you're not necessarily, and the reason would be this. The reason would be this. How do I get out of this? Let me hit escape. How do I close this? X. All right. Here is the reason. Let's do this. If I have a circuit breaker like this, and let's say that this is IARC max, and this is IARC minimum. The clearing time for both of those are exactly the same. So the higher incident energy will be based upon IARC max, which is why in this case, because both here's what's happening in this case. We have a fuse on the primary side of this transformer. And we'll say this is 2 seconds. And this is IARC max. And this is IARC min. The clearing time is exactly the same. So the calculation will be based upon the maximum arcing current, which is 21.95, 21,950 amps. At 2 seconds is going to give me a higher incident energy than 19,250 amps of arcing current at 2 seconds. Make sense? I'm glad Bill Cosby showed up. All right. Okay, what else? Okay, so let's go back to this. There was something else I wanted to okay, so now let's do this. Let's take, and what we did yesterday was we said, let's take this device and we are going to go to connections. We're going to disconnect. And we are going to clone this, cloning that conductor. And we're going to take the exact same conductor. And all we're going to do is we're going to do the same length. And we're splitting, we're putting this PD12 in its own enclosure now. Okay? So now we're taking PD12, putting it in its own enclosure outside of this bus. We're going to run the short circuit study. We added a little length of conductors so it reduces our fault current a little bit. But what does it do to our incident energy? Now look, that 100 and some calories at bus 4, bus 4 doesn't have two values anymore. Why? Because there's no main breaker in there, but it took the 106 down to 77.8 calories. And now what I can take advantage of, if I open PD12 and I go to settings and I put it in maintenance mode at 2.5 times setting, I take my calories down to 1.57 for the electrical worker. That's a safety by design principle. Popping out that secondary main breaker, instead of including it in the enclosure, take it into a separate enclosure, put the arc reduction maintenance switch on it, and I can reduce the incident energy. Now, the challenge is if, let's take a look at, let's just do this. Let's go to, I'm going to go to TCC. We're going to say 2000 amp breaker. So there's my 2000 amp breaker. Okay, so let's do this current times 10. I can't move my instantaneous. Now I could, this is a 2000 amp breaker. Let's do this. Let's try changing the breaker. Let's go back to the library. That's an RG breaker. What if I go to I'm going to go to a Magnum. I'll go to a Magnum. I'm going to go to a Magnum and I'm going to go to LSI. Let's go to this one. Magnum 520. Let's see what this does. Right, so, and I need, let's change it out, hold on. Library. I don't want 635, I want 600 volts. 600 volt Magnum. 2000 amps, right? There's 1600. Here's a 2000 amps, 520 trip unit. Is this it? I'll make sure, see if that's the same device. Yes, it is. So there's my trip curve. Now I need to change the, I need 480, 2000 amps, 2000. So there's my 2000 amps. I'm going to take this up to unity. So that's my 2000 amps. So I can't, I'm not going to get lower. Oh yeah. Okay. Yeah. Yep. See what I can do. I can push my instantaneous out and have a short time delay and do that. And watch my calories over here. My calories are going to 26.1. If I bring my short time delay down, bring my instantaneous over, I'm down to 3.45 calories. Now I'm at 3.45 calories. I haven't even included any arc reduction maintenance mode or anything like that. I'm down to 3.45 calories with a standard breaker all the time. As long as I don't have inrush currents from downstream equipment getting into this, this is around 4,000 amps. So that's about 2 times. So that's about 4,000 amps. If I move it up a little bit, I'm still at 3.45. I move it up, I'm still at 3.45. I'm still at 3.45. Still at 3.45. Now I went to 6.9. So right there, I could take this as high as around 16,000 amps. with this type of a trip curve, and I got a nice little delay for any inrush currents that are going on downstream, and I'm all the time at 3.45 calories. So now, but I went to a Magnum, and what's the difference? So I had an RD breaker before, which will be in a smaller piece of equipment, a smaller equipment, smaller footprint, all that jazz. And I went to a Magnum, which is a much bigger breaker, and I'm into a low voltage assembly. So the cost difference went up, but the value just from this is all the time. So if you know, in the RD breaker, I had to put it into maintenance mode to get you down to 1.5 calories. With this, I can be at 3.45 calories all the time, regardless. So if anything happens in that equipment when I'm not in maintenance mode, I will always have a low incident energy. So, but I had to buy a bigger breaker. I had to go to a more expensive trip unit, etc., to get me that flexibility and that functionality. Now, I bet you my application engineers in our sales offices will probably get you a better mix to get that addressed. But these are the things that you can do once you start playing with this one line diagram. So now we say, okay, I added a circuit breaker here. I have a little bit more conductor. I basically created a lower incident energy all the times, 3.45 calories. I can equip it with maintenance mode and get it to even something less than that with maintenance mode. But in any case, I have a much better design, and I also have a more expensive design, but that's okay, depending upon your budget, depending upon what's going on. I could go with the multi-case circuit breaker RD and put maintenance mode on it for my electrical worker. That's perfectly fine as well. And then you could go on and on all the ways down through to your other equipment. So this bus 7, which is down here, this bus 7 has a calories of, now I'm going to have two values here. Bus 7, based upon this overcurrent protective device, is 24.4 calories. Based upon this upstream overcurrent protective device is 28.1 calories. Now, what I could do on this HLD, I don't have, if I had a maintenance mode on there, I could possibly, if I put it on 5, lowering the instantaneous of that upstream device doesn't do me a hill of beans, other than possibly get me into a nuisance tripping issue with the downstream. Tom, is zone interlocking considered in arc flash studies? Okay, Ahmed, here's the thing with ZSI. ZSI, I've seen people include that in their incident energy analysis, but here is what you've got to figure out. So if you think about what's going on in a panel, let's say that I have a piece of equipment like this, and I have a main breaker, and I've got feeder breakers. Okay. What does zone selective interlocking do? I am going to be putting a data communication line between the upstream and downstream. If I have a fault here, here's what we do at this breaker. I want to make sure I explain this clearly. When you think about a circuit breaker, it's going to send a signal up when it sees a fault here. Okay? In many cases, I have seen when they're testing a circuit breaker, they'll take it out of the panel, they'll put current through it, and they'll have the long time settings and the short time settings, and they'll say, regardless of the current I put through it, it trips instantaneously. And the reason is because in a zone selectively interlocked system, there's a couple set of things. It is sending a signal up to the upstream device. So this is sending a signal up, but it's also listening down for a signal from downstream. If it's the last device in your series system, what we do is we jumper this back on itself. So when it sees a fault, it sees its own signal. So if I take this breaker out of the cell and I put it on a test bench, I'm going to want to take that and jumper it to itself so that it basically what happens is when a breaker sees, when I have a fault down here, this breaker, the fault current flows through that breaker and through that breaker. They both see the current. So this is A and this is B. Device A sees the fault and so does device B. So they're both triggered. Device A sees the fault. It looks at its signal. And it could be a 24-volt DC. It could be, depending upon the manufacturer, will tell you what signal is. And if it sees the signal there, then this breaker knows that the downstream breaker sees the fault as well. And then the breaker A is going to say, I'm going to go as I was programmed, which is based upon the trip curves that we were just looking at. So it's going to, if I programmed a 30 cycle delay, it's going to wait 30 cycles. The downstream breaker sees the fault. And as it's the last device in the system, I jumper the last one, because if I didn't jumper it, as soon as it went above the short time delay pickup, it's going to trip instantaneously. And that would not be good for selectively coordinated systems or any level of coordination, right? Because then I could have my last device in this trip instantaneously. So, where zone selective interlocking is beneficial and when it is used is when I have a fault in between these two devices. So device B does not see the fault. It does not send we call it a restraining signal. It does not send a signal to the upstream device A. A sees the fault, looks at its terminals for the restraining signal from the downstream device, doesn't see it, so it knows it's the last one in the series. It ignores all of your set points and trips instantaneously. Now, having said all of that, you know that when you zone selectively interlock two breakers or a series of breakers, your zone of protection is right here. If I have a fault downstream of the downstream device, and let's say it's got a 3-cycle delay, let's say it has a 30-cycle delay, 12-cycle delay, it's a big power breaker, I could have a plasma cloud that could possibly cause a line-side propagation. So technically, and I've seen people go either way on this. Some people will say, I'm going to label it based upon the incident energy, the clearing time of the zone selectively interlocked systems. But I've also seen engineers say, look, if I have this zone selectively interlocked and it's not interlocked with an upstream device, because what I could do, let's say that I have this going on. I've got an enclosure here, and I have an enclosure here. I could zone selectively interlock those two. I could zone selectively interlock those two. I could zone selectively interlock those two. In that case, the incident energy here is going to be dependent upon the clearing time of this, which will be the short time delay pickup setting and a clearing time of approximately 0.07 seconds. It'll be the clearing time of the short time delay, the fastest short time delay that you would have for that breaker. It's not instantaneous. It'll be the short time delay clearing time. So I can nest these, but if I'm not nesting it, if I don't have that going on and I zone selectively interlock these devices, the incident energy at this panel really is dependent upon the clearing time of that upstream overcurrent device, because I have to assume line side propagation on the line side lugs of those. And then it's based upon the upstream overcurrent device, even if I zone selectively interlock in that panel. But if I have a fault here, then it's going to clear very fast, but I don't have a standard that says because you've cleared so fast that you're not going to have that plasma cloud that's going to cause a line side propagation. Make sense? All right. All right, so we talked today a lot about this diagram, right? We picked our overcurrent devices. We talked about the ampacity. We did a conduit sizing. Do you think ZSI should be a permitted solution for 2487? Well, okay, Ryan, I have an opinion. My opinion on this is I think 24087 I like 24087, but I think it needs work. Here's where my thoughts are. 24087 and 23095. 23095 is GFPE protection of equipment, service equipment, and 24087 is really there for the electrical worker. Just based upon what we just said, if I have equipment with zone selectively interlocked, I don't have a complete protection for the electrical worker. That, in itself, inside that equipment, does not lower the incident energy for the electrical worker. Why? Because I've got a load side lug that's not protected. It's outside of the zone of protection. I have a line side lug that's outside of the zone of protection. If I put arms on the main in that equipment, I'm protected all the way down through the load side, but I still have that vulnerability on the line side, but now I have barriers which will reduce the likelihood. It's all about likelihood and severity. I can reduce the likelihood on the line side. So here's my thought process. I think that in 24087, zone selective interlocking, differential relaying are really about equipment protection. Not so much personnel protection. We've been using ZSI for years in petrochem facilities and pulp and paper and universities and things like that to, if there's a problem in the gear, we clear it really fast. I'm not calculating an incident energy based upon that clearing time, the upstream. So I think 23095, which is focused on equipment protection, should give you the ability to say, you can do GFPE, you can do zone selective interlocking, you can do arc quenching technology, you can do differential relaying. That's going to protect your equipment. We've been doing that for years. 24087 should be your arc reduction maintenance switch technologies, which will provide worker safety. And I think you need them both. You need to think about the continuous protection of the equipment so that if I have an internal fault, I clear it. But I also need to think about my electrical worker, and the arc reduction maintenance switch is the only technology that's going to look downstream. ZSI, unless you nest downstream, doesn't help downstream. Arc quenching technologies doesn't look downstream. It looks in the box. So in 24087, the technology that looks downstream is your arc reduction maintenance switch. Think about the success story I had with Ken White on at Olin Chemical where we had they were pulling conductors downstream. We had an arc reduction maintenance switch on the main that provided the clearing time all the ways downstream to where they were working. And instead of like a 20 calorie event, they were left with what they calculated to be like 2 point some calories, which ended up to be even faster of a clearing time. And it was the damage in the equipment. So it was hard to tell where the damage was about the size of a dime. They were able to re-energize and very quickly. And after a quick change of the pants, they were back home that evening. So, in my opinion, we got to look at 230.95, and we need to say that's about equipment protection of service entrance equipment. We need to think about moving that main overcurrent protected device, that service overcurrent protected device, in its own enclosure, and we need to think about looking downstream. So that's where my head's at now. I am. I'll tell you what, the hair on the back of some people's necks go up when I start talking like that. But I think you got to think about the electrical worker. You got to think about what is really protected. What are you using for your incident energy calculations? What is providing worker safety and what is providing equipment protection? And then I think only then will you start to get into the real core of providing equipment and personnel protection. All right, we are at 7:06, and we went for 2 hours. At the beginning, I didn't know if I was going to make it. I really didn't. I was absolutely exhausted. Today was a very rough day. We got the electrical safety workshop. We had committee meetings for that. I had to redo the book to get that over to them. I had 2 JATCs looking for wood core transformers. I have stuff I'm working on, curriculum. I had to get some questions done, and I have phone calls, and it was a busy day. I didn't think I was going to make it, but we did, and I got a lot more energy now. So hopefully you guys got something out of today's session. Now, what we are going to do next week, I want to get into ground fault current calculations, positive, negative, and zero sequence. And I want to calculate ground fault current. So what we're going to do is take this one line diagram and we're going to convert that over to a zero sequence, negative sequence, and positive sequence. And we're going to do the math. I'm going to use my equations. I'll pop it up there so you can download them ahead of time. And we can do the math together. I can help you understand my spreadsheet. And I'll tell you how to come up with those equations. Makes sense? And hopefully I'll see you guys and gals next Thursday at 5:00 p.m. Don't forget, subscribe. I want to get to 15,000 subscribers. We're on our way. I am a lot closer to that than I thought I was. So we're moving up in the subscriptions. So I appreciate you, Ryan, for dialing in. I thank you for your expertise in the code, and you too, Ahmed, and Mohammed, and not Bill Cosby, what else? We got Mohammed, we got MC. I'm not sure who MC is. That MC Hammer, James Smith. Thank you for dialing in, buddy. Robert, I know he's got a program, so he's probably doing that. Felix Sandoval, thank you for dialing in as well. I still got to show your steel conduit. Yes. Boy, this is good stuff. Boy, you guys are I appreciate everything you guys are doing and dialing in and hanging in there. So take care. Good night, everybody. Have a good evening. And I will see you next week at the electrical safety workshop. And I probably will still do a fast 1 hour 12 at Tuesday, 12 Eastern. I'll probably do a really quick one over there. Maybe that's where I'll give you the spreadsheet and prime you up and talk a little bit about what's going on at the electrical safety workshop. All right. Thanks, everybody. Good night. Take care. Stay safe. God bless. And please stay healthy. It's getting better, baby. That's right, Felix. It's getting better. Paul Costello, you're the man. Thanks for dialing in, Paul. Good night, everybody. Great job, Ryan. Everybody, really appreciate your help. So we are out of here. All right. Take care. Stay safe. God bless. Take care. Right. Thanks, Felix.